Okay. I logged into math the other day, and both you guys and the intro programming group are programming at least at the beginning of the semester using the same environment, and there are probably 12 or 13 people logged onto math. And the kinds of things that you're doing, math can totally handle that. But especially you guys may have the ability to, if not bring the machine down, certainly bring it to a grinding halt, like really slow it down. And so in an effort to avoid that problem, we actually like math.whitman.edu. We like math too, but math.whitman.edu is serving up web pages. It's doing some other mission critical kinds of things. And so I got WCTS to open up 6 computers in the lab to the outside world. So now all of the instructions I gave you for logging into math also apply to, let me show you. So also apply to from Phoebe down to Themis are now open to the outside world. And you can log into any one of these machines and create and edit files there, and they will automatically and instantaneously be distributed to the other machines. In fact, they're not really being distributed at all. It's that they're all mounting a central file server, and when you're logged in to say Phoebe and you make changes, you're making changes on that central file server. And then you log out of Phoebe and you log into Themis, and you're really just editing the same file. It's on the same computer. So you can use any one of those last 6 machines, not Zeus now, just Phoebe through Themis, any one of those machines interchangeably with math. And in fact, I would encourage you to use those instead of math. They're faster than math and probably going to be more lightly used. As is usual, you hop in, you have a look around. I have to, like Luke, are you logged into Nemosine right now? No. Okay, so you would finger at math, and you would see there's 2 people on Nemosine, and so you would choose Phoebe because there's nobody on Phoebe, and log in there and work there. Yeah.
So I was on Zeus and just SSH'd into Tethys, and now I'm logged on to both.
Yes.
How do I not do that?
What you should do is log out.
Okay.
So you've got this daisy chain going.
Yeah.
You should log out, and then log directly into. Yeah.
So is getting on math and then logging into one of these the same as just logging onto one of the
It's almost the same. There is this extra hop that you're introducing, which is on this network is going to have no effect. You are not going to see that. But for the sake of efficiency and sort of cleanliness, you might want to just dive straight directly to one of the machines. Because ultimately, when you're working on the command line, all you're really doing is pushing these little characters back and forth. Each character is a byte, and that's just not even measurable on the bandwidth that you have available to you. So it's not a big issue. That said, if you live on campus or you work on campus, any one of those machines is available to you. It's just that only Phoebe through Themis and math can be accessed from off-campus sites. If you're on campus, all of them are interchangeable. So if you're like now, you could jump onto Koos, however you say that, Cronus, Demeter. All of those would be empty and fair game, and they all have the exact same programming environment. Okay. So log into math, finger at math, have a look around, and then pick your machine. The syllabus for today. I don't want the YouTube, I want the... So I've updated the syllabus. I've introduced the first 2 readings in Gishard's book, sections 2.1 and 2.2, which discuss what we're going to be talking about today, the topic of linked lists, the first data structure that we'll explore. Along those lines, as I was reading, I've kind of tweaked HO1 a little bit, so be aware of that. Reread it. Probably not. None of you have really started this seriously, and if you have, it's not. They're not substantive changes. Just be aware that I've made some tweaks. Let's talk a little bit about that. Linked lists. That's what we want to do today. Linked lists. So, a really common thing to want to do in computing is to keep lists of things. And let's talk about a simple list of characters. So we're going to talk about linked lists. And to start off with, we want to start with a naive notion of lists. What is a list? It's some ordered collection of data. And from your personal experience, the simplest kind of list might be an array. All right, so let's pretend we've got this array of characters. And I'll just pick some at random here. So let's pretend that these guys are sitting in an array. And you know in C and C++, these arrays are indexed starting at 0. So there are 6 elements of this list, and they are indexed 0 to 5. Just arbitrary characters, X, A, V, D, F, and N. What are some things that you might want to do to a list of data in computer science? So you might want to sort this thing.
Append an entry.
Yep.
Insert an entry at a certain position.
Insert at a location, sure.
Check if something isn't lost.
You got pretty much all of them.
Pretty clever.
Yeah. There are a couple of, there's a Boolean that you might want to look at.
Empty.
Yeah, empty. So I'll put a question mark after that. Empty? If true, then it's empty.
Find out how many elements are in it.
Yeah, and that's the other one. Yep, the size. There may be others, but those are the biggies. If you decide to keep your lists in an array, some of these are hard and some of them are easy. Which of these operations do you think are hard for an array-based list? Hold on. So something that's hard for an array-based list is certainly sort. Insert is hard. Why is insert hard?
Because an array is a fixed size.
Yeah.
You gotta move it.
Because I have to move everything. Unless I'm appending. Appending's easy. But inserting is hard. Because I want to insert, say, a new character at slot 1, then everything from slot 1 to slot 5 has to go down 1, right? And that's a lot of work. What else is hard?
Checking to see if something's present.
Searching is hard, yeah. Yeah, sort, insert, search, remove. These guys are hard. What I'm going to do is present to you a data structure today called a linked list that makes at least two of these guys easy. So we're going to, a linked list makes insert and remove easy. Sort and search, about the same. Let me put parentheses around that. Okay, so the problem with an array-based list is the position, the element's position is sort of inexorably tied to the array index. So the problem here is tied to the array index. Walk much? All right. What we want to do with a linked list is we want to dissociate this problem. We want to separate the storage of the stuff, right? This is, the array was just a convenient way of storing the data, and just by doing the simple thing, we kind of locked ourselves into using the array to position the elements in the list. And we want to separate from this. We want to use our own position system. And the cost is that we have to allocate a second array. So we have the array of data, and then we have a second parallel array that tells you what the next element in the list is. So let me go back and write down the first array. So we have the array, the element array. And that's going to be this guy. So there's the element array and the corresponding array index, and then we have the next array. And I'm going to use a simple next array at the moment. 1, 2, 3, 4, 5, and -1. Okay, let's explain how this works. So, these guys are paired like this. And what it says is the first element of this list is X, and the next element is whatever's sitting at position 1 in the array. So that's A. So then you go to A, and that says that A is the piece of data there, and the next element in the list is whatever's sitting at position 2, which is V. And then whatever's sitting at position 3, D, and so on. And then you get down to N, which is the last element of the array. And what's the next element of the array? Well, there is no next element of the array. And so we have to have some kind of signal to indicate that we've reached the end of the list. I've written a -1 there. Why is that a convenient signal?
-1 is a valid index.
It can never be a valid array index. So if I hit a -1, I know I've reached the end of the list.
So the first number in the next array was a 3, then D.
Exactly. Well, I'm leaving a little bit out here. You need a little bit of additional information, which I'll call a head. And we'll say head equals 0. And this indicates the head of the list, the start. So the head is 0, which says, okay, X is the first element of the list. And then X, the next pointer for X is 1, so A. The next pointer for A is 2, V, and so on. All right, let's talk a little bit about what we can do with this and how we can manipulate these things. Let's pretend that we have this guy and we want to insert Q into the list between where do I want to do it? Between D and F. So we want to put Q right there. Now, the old way would be to slide F and N down, right? And stick Q in there. And that's a lot of work. The new way is to append Q to the element array. Append because it's easy to append, right? You know how many elements you have. Presumably you're keeping track of that somewhere. You know how many elements you have, and so you know where the next open slot is in the data array. So you just put it in there. No work at all. No sliding of stuff around. So we have X, A, V, D, F, N, and Q. And we have 0, 1, 2, 3, 4, 5, 6. So this is the new guy. As you might imagine, the real work in inserting this guy is tweaking the next array, the array of next elements. So let's do that. So I'm just going to rewrite the current array. And we'll put, let me put it closer, next, right here. So I'll just put 1, 2, 3, 4, 5, 6, oops, not 6, -1. So that's how it was before, right? Now, where did we want to put this? We wanted to put this between D and F. So the element after D is no longer indexed by 4, it's indexed by 6. What's the next pointer for Q? 4. And the next pointer for F stays the same, right? That's a hell of a lot easier. Well, actually, probably in this case, it's about the same because there's so few. But you can see that no matter where I decide to insert this new value, the work is exactly the same. I just throw it at the end of the element array, tweak a couple of values in the next array, and I'm done. I haven't had to slide, a whole bunch of elements forward or what have you to make space. This is a linked list.
So the only next array values that you have to change in this case are Q and the one before Q.
Yeah.
And then everything else stays the same.
Exactly. Yep. And this is just one example. You can read about it in David's book. There are lots of other things that you might want to do. For example, remove elements or swap elements or what have you. But the idea is the same. You don't actually move the elements around. You just move around these next pointers, and it's a lot easier. Other questions? Okay, the assignment that I'm giving you is not to do an array-based implementation. It turns out that this is sort of a useful academic exercise to understand linked lists. But the way to actually implement linked lists is using dynamic memory and nodes and pointers, actual pointers. We talked a little bit about pointers in C++ last spring. I'll talk a little bit more about them today. My hope is that you'll just kind of pick them up as we go along. I don't want to sort of spend a whole lot of time dwelling on pointers. I think you'll be okay. So typically, linked lists use pointers to indicate next element. And usually they're built out of nodes. Okay, what's a node? A node is a box. The top half of the box has data, and the bottom half of the box has a node pointer. Some sort of arrow that points to the next node. And a linked list might look like this. You have a bunch of boxes with data. And this guy maybe is the beginning, so we'll say we have a head pointer which points at this guy, and then inside this guy is a pointer that points at this guy, and inside here is maybe a pointer that points at this guy, and then in here is a pointer that points at this guy. And then here there's a pointer that maybe points to what we call null. And that's the end of the list. So you have these nodes just sort of freely floating in memory somewhere. You don't really know where they are. And the only way to get from one node to the next is to follow the next pointer. So you start at the head, and that tells you where the first element of the array of the list is. And you go to that first guy, and then you dive into it, and you grab the next pointer, and that tells you where the next guy is. And you dive into that, and you find the next pointer, that tells you where the next guy is. There are some difficult things about this. For example, one of the things that's difficult about it is it's hard to jump to the third node. The only way to get to the third node is to go through the first node to the second node, from the second node to the third node. Because there's no way to get directly to the third node. It's one of the limitations of linked lists. There are ways around this, but that's definitely something that you want to think about. The only way to get into this list is through the head pointer. Start at the beginning and follow the links. If, God forbid, you accidentally delete your head pointer, then your list is gone. It's still there in memory, but you have no idea how to get to it. All right. The top half of the box we almost don't care about at this point. We're much more interested in the data structure than we are in the data. So the top half of this box can have ints or doubles or whole classes or objects and classes, excuse me. It can have anything you want really in there. What we care about is the linked list structure. And what are some of the limitations of linked lists? And what are some of the valuable parts of a linked list? For example, let's say I want to insert a node between these two guys, between this guy and this guy. I want to insert a node. So I create the new node. Let's put it up here. I don't really know where it's going to go. I create the new node. I copy this pointer to here. I make sure I do that first. So I copy this pointer to here. And then I point this guy there. I find this much easier to think about than the array-based version that I was talking about earlier, where you're moving around array indices and so forth. I like to think about these boxed pairs and then just arrows that connect them in some way. This is by no means the only kind of linked list that you can build. There are so-called doubly linked lists, where not only do you have a next pointer, but you have a previous pointer. So not only do you know where the next guy in the list is, but you know where the previous guy is. This is useful if you want to go back and forth a lot in your list. And there are lots of variations on the theme. And the nodes in a situation like that would be 3 boxes. 1 box for the data, 1 box for the next pointer, 1 box for the previous pointer. This is a really important topic, this idea of node, because most of the data structures that we're going to work with in class this semester are going to be built of nodes like this. It won't surprise you to learn that I can build a tree-based structure, like a binary tree, out of such things. Right? I can have a node with 3 boxes. 1 box has data in it. The left box points to the left child. The right box points to the right child. And suddenly I've got a big binary tree. And it doesn't have to be a binary tree. It could be a trinary tree or a tertiary tree or what have you. I can put as many pointers and arrows in there as I want. And I can have links that go down to children, and I can have a link that points up to ancestors, parents. So this idea of a node with some data and some arrows in it, some pointers, is really the foundation. It's the atom of data structures. It's what almost all data structures are built out of. Some kind of node with some data and some arrows pointing places. But we're just going to keep it simple today and work with linked lists. What I'd like to do is move to a text editor here and code some simple exercises, some simple things. It's just really cool. List traversals and inserting and so forth. And also, at the same time, hopefully get you comfortable with some of the syntax, especially the pointer syntax, which some of you may not have even seen. It's in Savage, though. So, all right, so we go to math here. Maybe I want to go to Caret, actually. Did I go back to math? I can barely see the, yeah, there we go. From this angle, I can hardly see the screen. Come on. Wake up, Caret. Okay, I'm going to start putting things in an example directory for you guys that'll be available on the web page. And this will be there. I think, yeah, there's the linked list directory. I was actually practicing this morning, so I'm just going to start from scratch. It's been a while since I taught this stuff, so I had to kind of dredge up some old techniques. All right, so here's a linked list. What I want to do is I'm going to build you a node, something that we can build these little boxes out of, and then I'm going to write a main program and a function that will append stuff to the list. And we'll talk about other things as they come up. So instead of writing a node class, which is something that we'll start doing later, let's just keep it simple and build a node struct. And this guy is going to contain a character, and it's going to contain a node pointer called next. It's really weird, you know. The struct contains a pointer to something of the same type. It might seem like it's circular, but it's okay.
Why? I mean, is it possible to just have it as a pointer as opposed to a node pointer, or is like having it be a node pointer required?
The way that I'm about to do it, it's required, and you'll see in a minute why. What I'm going to do, the reason it's required is I'm going to start using C++'s dynamic memory allocation. I'm going to start creating nodes on the fly and deleting nodes when I'm done with them. And whenever I create a node, what C++ gives me is a pointer to that new node. And that's how I have access to it. So what do I mean by creating a node and a pointer? Remember that, or maybe you don't remember, you should know. Let me go back here and let's talk a little bit about memory in a computer. So in this computer, in those computers, the system memory, right? You have 4 gigabytes of RAM or whatever. That RAM is really just 4 billion bytes, all lined up linearly. And there's a first byte with memory address 0 and a second byte, memory address 1, all the way down to the last byte, memory address 4 billion, whatever. So it looks like this. And they can be stored in whatever, but how you feed them to how you refer to them in different contexts, sometimes it can be hex. It's often hex. So here's your main memory, and it's almost perfectly analogous to an array of bytes. These are memory addresses. And it's interesting, that 0 byte or that 1 byte, that refers to an actual physical piece of that machine. And that byte, if you put something in it, you're literally playing around with that piece of the machine. So you're at the hardware level here. When I allocate a node, what is going to happen is the operating system is going to go out to the main memory and it's going to carve out a section for the node. And it's going to return the index of the first byte. That value is the pointer. It tells the machine where that new node is. And you store that information in pointer variables. Back here in my program, node star is a pointer variable. The variable next will have an actual physical hardware address. I'm kind of lying to you because of the way the operating system works. Users access memory in kind of their own abstract layer. So it's not really directly on the hardware, but it's as close as you're going to get. So that next thing is actually an index of the first byte of whatever node it's pointing to.
So we can do notice or another variable. And then what does the asterisk indicate?
That means that it's a pointer instead of an actual node.
Okay.
Okay, and it's where the node is instead of the actual node. I promise you'll get used to it. All right, let's keep going. So there are a couple things that are useful when you're writing instructional programs like this. You'd like to have some input-output. Like I'd like to be able to print some stuff to the screen, and so you include I/O stream so that you can get access to see in and see out. Remember that? Okay. Another one when you're working with pointers is see standard definitions. What this provides you is the null definition. Whenever you have an uninitialized pointer, you should set it to null. Question, Evan?
Since we're writing this program across 3 files, do those only go in that header, or do they go in all 3?
So let's say you're writing. What I'm going to ask you to do is write a list class. And I'm actually going to give you the list header. If you put it in the top of the list header, you're going to include that in list.cpp, which means that stuff gets transmitted into list.cpp. And you're going to also include that guy in main.cpp. And so that stuff's going to get read into. So if you put it in the .h file, wherever you use that .h file, it's going to suck this stuff in. All right. The beginning of the list we typically call head, and it's going to be a node star. And when I first define this thing, it's a node star pointer. I'm going to set it to null because it's not actually pointing at anything. This is really useful. It's a good practice to get into when your pointers are not pointing at anything meaningful. They should be set to null. When you're programming, you do a lot of editing and then a lot of testing. I encourage you to have at least 2 windows open. One for editing and one for compiling and running. And I also encourage you to write a little bit and compile. In fact, you should make it a practice to always work from a file that compiles. So right now, list.cpp compiles. I don't have to worry about any kind of syntax errors, so I can go on. All right, this guy is a pointer, but it's not currently pointing at anything. What I'd like to do is append. I want to write a function that appends something to the list. So this is going to be a void function. I'm going to call it append. It's going to take a piece of data, and it's going to take a node star pointer. Yep. Let's call this guy, I don't know, P. Okay. The ampersand means that the argument in that slot is passed by reference, which means that this function is able to modify that argument in the calling program. I want to allow this function to be able to modify P, whatever that argument is, and I'll explain why in a second. I want to append a character to the list. The first thing that we have to worry about here is the special case when there's nothing in the list. So if P is null, I have to do something slightly different. So if P is null, I first have to get my hands on a new node. So I'm going to give myself a node star, new node. This is a local variable that is able to point at a node. And I'm going to allocate a new node. So, some of you, probably most of you, are not really familiar with this new operator. The new operator goes out to the operating system and says, hey, I need some memory for one of these node structs. The operating system, and it actually says how much it needs. So it's going to ask for a byte for the character, and it's going to ask for 4 bytes for the node pointer, or 8 bytes if it's a 64-bit computer. So if it's a 32-bit computer, it'll ask for 4 bytes. If it's a 64-bit computer, it'll ask for 8 bytes. And you don't need to worry about that. That's something that happens. So it goes out to the operating system and says, hey, I need one of these new nodes, one of these boxes, with a data box and a pointer box. And the operating system says, sure, we've got some space over here. Very nice. I'll get you a byte for the character, and here's 4 bytes for the pointer. Here you go. Here's where it is. Here's the address. So the new operator comes back with an address, the address of this new memory. And where does the address go? It goes into the new node. And the new node is a node star. It's a pointer. It's able to hold memory addresses. All right. Yeah.
So the node star means that pointer can only ever point to nodes?
Yes.
Okay.
The compiler will yell at you if you try to point it at anything else, even though all pointers are addresses and all addresses are either 4 bytes or 8 bytes. So it's really just a check for the programmer that the programmer knows what they're doing. What I want to do is set the value of this new node. Okay, that dash and greater than sign. That's called the, gosh, I think it's called the deref. No, it's not the dereference. It's like member selection operator, I think is what it's called. I should know this, but I don't remember off the top of my head. What this does is it reaches into the, it dereferences new node. So instead of being the address, it now becomes the actual box. And it reaches into the box and grabs the x variable. And it sets it to the value x, which is the argument that came in.
So what's the difference between just creating an object in the old-fashioned way? Node, current, and then grab x.
Rephrase.
Okay, so you use the new keyword to
Yes.
get your hand on a pointer of the node as you create it.
Yes.
And then you use weird arrow to get the x value of the node you just created.
Yes.
Why can't you just say node, my new node, and then get the pointer and then get the x value?
Like declare a node somewhere and then just get the address of it?
Yeah.
Because that's kind of a static operation, right? I could declare the node up at the top, say. Boy, what's a good way of... So I think what Evan is getting at is I would declare, say, a node struct locally. like node n. So maybe I would go right in here and I would say node n. And then that is surely going to allocate a node, and that variable is now not a pointer to a node, but an actual honest to goodness node. All right. Now, that guy has an address. So I could say if p is equal to null, just let p equal the address of n. And now p is pointing at an honest to goodness node. What's going to happen is when the function append quits, when it exits, it's going to clear out all of its local variables, and p is not going to be pointing at anything anymore. So you have to use this new operator in order to get persistent access to memory. Okay, so if the list is empty, that's really what we're dealing with here. If the list is empty, then the head pointer that I pass in is going to be null, and I need to deal with that. So if it's null, I make a new node. I set the data value to whatever the value should be. I set the next pointer to null because this is the first guy in the list. There's nothing after it, right? And the way that we're going to indicate that the end of the list is the next pointer for the last element points to null. And then I set p equal to new node. I could have sort of avoided the use of this intermediary new node, but I'm going to use new node in the second half of this if statement. Let's pretend that p is not null. So that means there's already some stuff in this list. This is append. It's going to put the newest element at the end of the list. I have to get to the end of the list. This is cool. You'll like this. Oh, and I'm kind of violating my own advice here. Yes. Line 21.
Yeah.
Oh, yeah. That's unfortunate. All right. I think it's lowercase in your homework assignment. Yeah. Thank you. This is really cool. Let's let cursor... Yeah, let's do this. Cursor. I could do it with a for loop or a while loop. Let's do a for loop. Cursor equals p. Cursor not equal, sorry, cursor next. No, let's do a while loop. I think it makes more sense. Fun stuff. So P is the beginning of the list. It's a pointer to the beginning of the list. In fact, I wish I'd called it head instead of P. If head is null, we're just going to create a new node and point head at it and walk away. If head is not null, that means there's stuff on the list. So now I invent this, I build myself this cursor thing, and I started out as pointing to the first node, right? Because P is secretly the beginning, points to the beginning. And then I say, while cursor next is not null, advance the cursor. Cursor equals cursor next. And I'm going to keep doing that until I get to the last node, right? And the last node, when I do cursor equals cursor next, I get to the last node, and then I check cursor next. That's the last node, so cursor next is null, right? So that loop exits, and now where is cursor pointing? To what is currently the last node. And now I build myself a new node.
Why does cursor equal P instead of head?
Because it's what I handed the function. And when I use it, I'll actually use it with head. And I should have done that to begin with, but
So you'll always pass in head.
in this case, yes. Yeah. And like I said, I'm doing this on the fly. So, so new node. Now, what do I want to do? This new node is after the current node that you're pointing at, right? So the first thing you want to do is put the data in there. Now, what's the next pointer of this new node? No, because it's the last guy. I'm appending it to the list. What else do I have to do to get this guy in the list? Something has to point to it. Who has to point to it? Yeah, the current, right? So cursor is pointing to the current last element. So how do I have to modify that last element? We know that the cursor is pointing to a node whose next pointer is what? Is null at the moment. That's why the loop stopped. What does it have to be, that next pointer?
Next.
It has to be not next. It has to be new node. And I think we're done. I know I'm over time, but it's just too good to stop. Let's do append x. Oh, and I've got to give it head too. All right, so append x to the list that is pointed to by head. And I also have to print it out, so let me get myself a cursor. And we'll do cursor equals head while cursor, gosh, let me think about this for a second. Let's try not equal to null. Yeah. Oh, and I have to advance the cursor as well. So while
You didn't head doesn't have a value actually.
head will have a value when after append.
Oh, that's right.
And you can see why I had to pass this node star by reference. Because the first time I call it on an empty list, it has to update P. It has to update head. I think this will work. Again, I'm flying by the seat of my pants because I'm out of time. Oh, forgot the using namespace. Yay. And then it's the most complicated printing of X I've ever done. Let me do A and run it. You know, you got to admit that's cool. It's amazing that, you know, all I'm doing is printing X and A. This is not a really great program, and I'll talk a little bit more about this right now. I am what's the word? Leaking memory, because I'm allocating memory and I'm not returning it to the system. So we'll talk a little bit more about that on Friday, and more about this in general on Friday. This is in the examples directory if you want to look at it. I know there's a lot here. Read about pointers and stuff in Savage. That's why you have Savage, because it talks about all that kind of stuff.